Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
Welcome to Module GL403, Formation Evaluation Using Well Log Measurements. You will recall that in our previous two wireline logging modules, GL401 and 402, we examined how wireline logging is conducted and how common downhole tools operate. In this module, we'll work with log data and see what it can tell us about a subsurface formation in terms of its water saturation, and finally, the producibility of a reservoir in terms of its relative permeability.
Wireline logs are used for a number of purposes. For example, for well-to-well correlations and construction of cross-sections, for subsurface facies analysis, for construction of synthetic seismograms, to provide data for subsurface structural and stratigraphic mapping, and to determine subsurface pressures and the presence of fractures. In this module, however, we will concern ourselves solely with the quantitative analysis of logs, often referred to as formation evaluation. Our objective in the quantitative analysis of well logs is to define the type of reservoir in terms of its lithology, the storage content of the reservoir in terms of its porosity, and the fluid type and content of a reservoir, whether hydrocarbon or water.
Now let's look at some of the common logs.
Nearly every well log includes on the left track of the log a spontaneous potential, or SP curve, or a gamma ray log. On some displays, both the SP and gamma ray logs are recorded together. We saw in video module GL402 how the SP curve results from naturally occurring electrical currents flowing between the borehole mud and the formation. The movement of ions, which causes SP currents, is possible only in formations with some permeability. However, there is no direct relationship between the value of permeability or even porosity on one hand and the magnitude of the SP deflection on the other hand. Let's examine a few basic relationships. First, we see that the SP curve is scaled in millivolts, with each division of the scale usually representing 20 millivolts. A negative reading will cause a deflection to the left, and a positive reading will cause the curve to deflect to the right. In the case of a freshwater mud and saline formation waters, the potential observed opposite, say a permeable sandstone bed, is negative compared to the potential opposite shale. Thus, the SP curve will deflect to the left. If the salinity of the mud filtrate is greater than that of the formation water, say in the case of freshwater sands, a positive potential is developed and the SP curve will deflect to the right. If the salinities of the formation water and mud filtrate are similar, such as when saltwater-based drilling muds are used, there is no SP current flow and thus no SP deflection opposite a permeable bed. The SP deflection opposite a thick, clean, permeable formation approaches a value called the static SP, or SSP. The value of the static SP can be found by drawing a line through the SP opposite the thick, permeable formation and another line through the SP opposite the intervening shale beds. The difference in millivolts between these two lines is the static SP. The gamma ray log is a measurement of the natural radioactivity of the formation. Because radioactive elements tend to be concentrated in shales, the gamma ray normally reflects the shale content of the formations. The gamma ray log is scaled in gamma API units of radioactivity, with high readings causing a deflection of the curve to the right, and low radioactivity causing a deflection to the left. Thus, high readings indicate shale, and low readings indicate clean, non-shaly formations, like sandstone, limestone, and dolomite. However, a clean shale-free sandstone may also produce a high gamma-ray response if the sandstone contains micas, potassium feldspars, glauconite, or uranium-rich formation waters. Thus, the presence of a clean sandstone can be overlooked if it contains one of these radioactive contaminants. If radioactive contamination is suspected, a type of log called a gamma-ray spectral log can be run that breaks the natural radioactivity of a formation in concentrations of potassium, thorium, and uranium. We'll take a closer look at this type of log later in the video. In quantitative formation evaluation, SP and gamma ray curves are used to determine potentially porous and permeable reservoir rocks like sandstone, limestone, and dolomite from non-permeable clays and shales. Another important use is to define bed boundaries. Note that the boundary of a bed is picked at the inflection point along the log curve. A qualitative indication of shale content in a formation may be determined by the amount of curve deflection between the shale baseline and the SSP in the case of the SP curve, and between the shale baseline and a shale-free clean formation on a gamma ray log. For example, on an SP log, a sand formation with an SP deflection about midway between the shale baseline and the static SP value, as displayed by a thick permeable sand, likely contains an appreciable quantity of shale.
Now that we've had a look at the SP and gamma ray logs, let's examine how logs can provide us with a quantitative determination of formation porosity.
The three common porosity tools are the formation density log, compensated neutron log, and the acoustic or sonic log. These tools are sensitive to both rock matrix and to the fluid filling the pore space. Consequently, their measurements reflect not only porosity, but also the type of rock, the clay content, and the fluid type. Let's start our discussion of porosity evaluation with the density log. We recall from GL402 that the response of the density tool is determined by the number of electrons per cubic centimeter of formation rock, referred to as the electron density. Electron density, in turn, is related to the bulk density of the formation. Factors which determine the true bulk density are the density of the matrix material, the formation porosity, and the density of the fluid filling the pore spaces. On a typical density log, scaling is from 2.0 to 3.0 grams per cubic centimeter from left to right across the top of the log, or for 20 divisions. Each division thus represents 0.05 grams per cubic centimeter. On this basis, it is a simple matter to find the bulk density in grams per cubic centimeter. Clean sandstone with zero porosity has a bulk density of 2.65 grams per cubic centimeter, and any reading with less than 2.65 grams per cubic centimeter in a sandstone indicates at least some porosity. A clean limestone has a bulk density of 2.71 grams per cubic centimeter, and a bulk density reading less than 2.71 grams per cubic centimeter likewise indicates the presence of porosity. In clean formations of known matrix density, porosity may be calculated from this formula. Porosity, phi, equals the known matrix density minus the log density, divided by the known matrix density minus the density of the fluid within the pore space. Because of the relatively shallow investigation of the density tool, this fluid is mostly mud filtrate that usually has a density ranging from slightly less than 1 to about 1.2, depending upon its salinity, temperature, and pressure. Rather than perform the calculation, we can easily use this chart to obtain porosity from the density log. The chart is designed to solve for porosity in three basic rock types: clean sandstone with a matrix density of 2.65, clean limestone with a matrix density of 2.71, and clean dolomite with a matrix density of 2.87. Let's examine a density log and determine porosity from the chart, assuming a clean sandstone as defined by the gamma ray log, and freshwater mud filtrate with a density of 1. At the depth of 7,534 feet, we read a bulk density of 2.35. Going up to the clean sandstone line and then across to the porosity scale for a pore fluid density of 1, we read 18% porosity, or we may refer to this as 18 porosity units.
On the log, an actual density porosity curve may be recorded. This curve is a continuous solution of the porosity equation using preset values for matrix density and fluid density according to conditions.
On this log, the density porosity scale reads from minus 10% porosity on the right to 30% porosity on the left, with each division therefore representing 2% porosity. Note that the heading specifying the matrix density used in calculating the porosity curve is in this case 2.71 grams per cubic centimeter, the matrix density for limestone. Thus, our porosity readings are only valid for limestone formations. In this case, we have determined from well cuttings that the formation defined by the low gamma ray reading from here to here is limestone. We thus read a porosity of 5.5% here and about 12% here. Now, let's go on to look at another common porosity tool, the neutron log. We recall that the neutron log responds primarily to hydrogen atoms in the formation. The two elements of a formation with the greatest concentration of hydrogen atoms are water and liquid hydrocarbons that occupy the pore spaces. Thus, in clean formations, the tool reflects the amount of liquid-filled porosity. Neutron porosity readings are computed automatically and displayed as a curve scaled in linear porosity units similar to the density porosity display. Neutron readings are affected to some extent by the lithology of the matrix rock. Therefore, a matrix setting must be chosen prior to logging the well. Neutron logs, however, are usually scaled for a limestone matrix, and if the actual lithology coincides with this chosen matrix setting, porosity may be read directly from the log. We know from cuttings information that this formation is limestone. Thus, here we can read porosities directly from the log, 5.5% here and 13% here. Porosities for lithologies other than limestone may be determined from a chart, but the actual lithology must be known. Let's look at a compensated neutron log run over an interval that we have determined from other data to be sandstone. First, we note that the log is scaled for a limestone matrix. We therefore cannot read porosity directly from the log, and we must use a chart. Here, our curve reads 15% apparent limestone neutron porosity. On our chart, we go up from 15% on the apparent porosity scale until we intersect the sandstone line, then across to find the true neutron porosity for sandstone, which in this case is about 19.5%.
Two common situations will cause the neutron porosity log to give false readings. These are the occurrence of gas and the presence of shale in the formation.
Water and liquid hydrocarbons contain about the same amount of hydrogen per unit volume. Gas, however, usually has a significantly lower hydrogen concentration than these liquids. Therefore, when gas is present in the pore spaces, the neutron log reads a too low porosity. In addition to seeing the water in the pore spaces of a formation, the neutron log also responds to the bound water associated with shales. In general, shales have a large apparent porosity because of their significant hydrogen content. This causes the apparent neutron porosity of shaly formations to be greater than the actual effective porosity, as indicated here by the density log. Often we can run a combination of porosity devices into the well bore together, thus allowing us to define porosity better than by using any single porosity device by itself. The most common pair is the density-neutron combination. This density-neutron combination log was run in a sand-shale interval in a South Louisiana well. The neutron porosity and density porosity curves were run on the same matrix, in this case a sandstone matrix, and the scales are identical. Thus, in a clean, water-bearing sandstone, we should expect the curves to match each other fairly closely. Let's take a close look. Above the sandstone in the shale, the neutron log reads a too high porosity of about 40 to 45%, as it responds to the high water content of the shales. From here to here, the neutron curve falls back to about 30 porosity units, while the density curve remains at about 15%, indicating relatively less shale. The zone is interpreted to be a silty shale or possibly a limey shale. The top of a sand body is indicated at a depth of 12,375 feet by the abrupt decrease in the gamma ray reading. A thin 2-foot interval of porosity is shown at the top of the sand, where the porosity curves average about 23% porosity. Then just below a thin low porosity bed, the two curves exhibit a marked reversal, with the density curve reading a high porosity value here of about 38%, and the neutron curve here reading a relatively low value of about 20%. We recall that the presence of gas, which has a considerably lower hydrogen concentration than water or liquid hydrocarbon, will cause the neutron curve to read too low. Also, the low density of gas compared to water or oil will cause the density curve to read too high. Thus, this type of curve separation on the neutron density combination log is often an excellent indication of gas. On our example, the separation extends more or less continuously from 12,380 feet to 12,408 feet, indicating a gas column of 28 feet. Adding this to the 2-foot interval of porosity at the top of the sand gives us a total net pay column of 30 feet. The curve separation is less over the bottom 10 feet of the gas column, indicating a transition zone to the underlying liquid column. The suspected presence of gas causing the separation of the neutron and density curves in our South Louisiana well tends to distort porosity readings. In such cases, charts for porosity determination become unreliable. One quick-look method is provided by the relationship where gas-filled porosity equals the square root of the neutron porosity squared plus the density porosity squared divided by 2. Thus, the formation porosity here at 12,283 feet is the square root of 0.20 squared plus 0.38 squared divided by 2, which equals 0.304 or 30.4%, close to the average of the two porosity readings. From the base of the gas column here at 12,408 feet to the bottom of the log, the two curves should essentially match, as we would expect in a liquid-filled sandstone, since both curves were run on a sandstone matrix. However, the neutron curve in many intervals, as we see here, reads a higher porosity than the density curve. This results from the neutron log responding to bound water in clays interspersed throughout the sand body.
We'll examine how such shaly sands are evaluated later on in this video.
Now, let's examine porosity determination from the combination neutron density log run over a West Texas carbonate. Both curves were run on a limestone porosity index with a scale from 0 to 30%. First, note the clean carbonate formation established by the low gamma ray reading, from here to here. The dashed neutron curve here closely matches the density porosity curve, thus indicating a limestone lithology, and the apparent porosity is 5.5%. From 5,050 feet to about 5,078 feet, we see an increase in porosity, with the neutron curve reading about 2 porosity units higher than the density curve. At 5,075 feet, the neutron curve reads 15% porosity, and the density curve reads 11% porosity. Placing these values on a cross-plot chart of neutron density porosity constructed for limestone porosity and saltwater drilling mud indicates a porosity of about 13.5% and a lithology of slightly dolomited limestone.
Now let's turn our attention to another common type of porosity log, the acoustic or sonic log.
Although in reality acoustic tools are more complicated than this, the tool in its simplest form operates by sending a sound pulse from a transmitter that passes through the formation and is picked up at a receiver at the other end of the tool. The sonic log records the time, t, required for a sound wave to traverse a given distance of formation. In the English system, 1 foot. Known as the interval transit time and presented in microseconds per foot, this value depends on the lithology and porosity of the formation. For a given formation, the interval transit time or slowness increases with increased porosity. Porosity from the acoustic log may be estimated from this chart based on empirical observations. The lines on the chart correspond to the matrix acoustic velocities of common reservoir rocks, and the chart is only valid for consolidated formations and when the fluid in the pore space is water or dead oil. In unconsolidated sands, the sonic log will read more than the true porosity. Thus, a special chart must be used that contains compaction corrections. Gas in the formation will also tend to slow the sonic waves, resulting in the log reading more than the true porosity. Here we see an acoustic log taken through an interval of sandstone. The top of the sand body is defined by deflection of the SP curve here at 12,112 feet. From other data we have determined that gas occurs in 3 porosity zones, and that a gas-water contact exists here at 12,142 feet. The acoustic log is scaled from 50 microseconds per foot to 150 microseconds per foot. Since travel time increases to the left, thus porosity also increases to the left. Here in the effective gas column, we read a travel time of 122 microseconds. Using our chart for a consolidated sandstone gives us a porosity value of 38%. Remember that gas in the formation will tend to slow the sonic waves, resulting in the log reading more than true porosity. Note that travel times are generally faster in the water-saturated sand below the gas column, averaging about 100 microseconds. Using our chart again, this reading gives us a porosity value of 31%, which is closer to the true porosity value of the sand compared to the high porosity value determined in the gas column. The sonic waves passing through the formation tend to find the fastest path through the rock matrix and around fluid-filled bugs and fractures. Thus, the acoustic log tends to ignore secondary porosity of this type and measures only primary or intergranular porosity.
Let's now examine how logs can be used to interpret lithology. The most useful logs for this purpose are the gamma-ray spectral log and the three porosity logs, density, neutron, and acoustic.
The gamma-ray spectral log measures the concentration of the three radioactive elements, potassium, thorium, and uranium, that make up nearly the total gamma radiation encountered in rock formations. In the right-hand tracks, the thorium and uranium concentrations are presented in parts per million, and the potassium concentration in percent. In the left-hand track, the total gamma-ray activity is displayed, scaled in API units. Ratios of the three elemental concentrations can be used as an indicator of formation properties. The thorium-uranium ratio, for example, varies with the environment of deposition. It is highest for sediments deposited in continental oxidizing environments, and lowest for marine reducing environments. High uranium-potassium ratios in shale indicate potential source rock. The thorium-potassium ratio has proved useful in typing clays. The ratio increases from glauconite, then to illite, to mixed-layer clays, to kaolinite chlorite.
If the formation consists of only two minerals, readings from porosity logs, when cross-plotted against each other, can provide useful information on lithology. These are the same cross-plots, by the way, we used previously to determine porosity.
On this log, the neutron curve is displayed as apparent limestone porosity, and the density porosity curve is based on a limestone matrix of 2.71 grams per cubic centimeter. Throughout this interval, the curves essentially match, with near identical readings, indicating limestone with a porosity of between 2 and 4%. In this interval, the gamma-ray reading indicates shale, which is likely responsible for the high neutron reading. Here, however, the low gamma reading indicates an absence of shale, yet we have a relatively high neutron porosity reading. Here we read a neutron porosity of 13% and a density porosity of 8.5%. Placing these values on our cross-plot, we establish a point here which falls about 1/4 the distance from the limestone line towards the dolomite line, thus indicating the formation is 75% limestone and 25% dolomite.
In addition to the neutron density cross-plot we have just looked at, you will find cross-plots of the neutron sonic and density sonic in your manual, as well as in service company publications. Now, these cross-plots can also be useful in identifying basic reservoir rock types. Also, you'll find other methods for determining lithology that use readings from the lithodensity log cross-plotted against various combinations of data from the basic porosity logs. These methods allow one to determine the relative combinations of up to 3 basic minerals in a rock matrix. Now let's examine perhaps one of the most important aspects of formation evaluation, determining the fluid saturation of a formation. In our previous module, GL402, on well logging tools and techniques, some fundamentals of water saturation, borehole environment, and formation resistivity were examined. Let's quickly review some of these basic concepts.
The saturation of a formation is the fraction of its pore volume occupied by fluid. Water saturation, referred to by the symbol S sub W, is defined as the fraction of the pore volume occupied by water. If water saturation is less than 100%, it is implied that the remaining pore volume is occupied by hydrocarbons. Hydrocarbon saturation, referred to as S sub O for oil saturation and S sub G for gas saturation, therefore equals 100% less the water saturation, or 1 minus S sub W. The water saturation can vary from 100% to only a few percent, but it is seldom, if ever, zero, because there is always a small amount of capillary water coating the rock grains. This capillary water saturation that cannot be displaced by hydrocarbons is known as irreducible or connate water saturation. A formation whose saturation is only irreducible water will produce water-free hydrocarbons. In a reservoir, there is usually a gradual transition zone from mostly hydrocarbon to 100% water. Within the transition interval, some water will be produced, the amount of water production increasing as the water saturation increases. Below the transition interval, water saturation is 100%, and therefore only water will be produced. Now, let's turn our attention to the electrical properties of formations. The dry rock matrix of most formations will not conduct electricity. Thus, dry formations have zero conductivity, or to put it another way, infinite resistivity. Electrical currents flow only through the water in the pore spaces of the formation, and then only if the water contains dissolved salts. The greater the salt content of the formation water, the lower its resistivity, and therefore the lower the resistivity of the formation. Most formation waters contain fairly high concentrations of salts. Therefore, the greater the porosity of the formation, and thus the greater the amount of formation water, the lower the resistivity. Let's now examine the borehole environment, looking down at a horizontal section of a borehole drilled through a permeable water-bearing formation. Mud filtrate is forced into a permeable formation by the pressure differential between the mud column and the formation. This forms a solid mud cake on the borehole wall. The mud cake usually has a very low permeability, and once formed it reduces further invasion of the mud filtrate. Adjacent to the borehole, most of the original formation water and most of the hydrocarbons, if present, may be flushed away by the filtrate. This zone is known as the flushed zone. Farther from the borehole, the displacement of the formation fluids is gradually less complete, resulting in a transition zone between mud filtrate saturation and original formation fluid saturation. This zone is known as the transition or invaded zone. The extent of the flushed and invaded zones depends on many factors, including the nature of the drilling mud, the formation porosity and permeability, the pressure differential between mud column and formation, and the time since the formation was first drilled. Generally, very porous and permeable formations are seldom deeply invaded. This is because initial rapid invasion causes an impermeable mud cake to quickly develop. Here we see some common symbols used in formation evaluation. The resistivity of the mud is referred to as R sub m. The resistivity of the mud cake as R sub mc. The resistivity of the flushed zone is R sub xo. The resistivity of the mud filtrate within the flushed zone is referred to as R sub mf, and the water saturation in the flushed zone is referred to as S sub xo. Remember, when using these symbols, the flushed zone is referred to by the subscript xo. The resistivity of the transition zone is referred to as R sub I. In the uninvaded zone, the true formation resistivity is referred to as R sub T. The resistivity of the water is referred to as R sub W, and the saturation of the uninvaded zone is referred to as S sub W. A common case is where a borehole with freshwater mud penetrates a water-bearing permeable formation containing saline formation water. Thus, the resistivity of the mud filtrate, R sub mf, is greater than the formation water resistivity, R sub W. A profile of resistivity outward from the borehole, in this case, shows the presence of mud filtrate, causing a high resistivity in the flushed zone, R sub xo. Resistivity then gradually decreases in the transition zone until it reaches R sub T, the resistivity of the uninvaded zone, which is low due to the presence of saline formation water. The symbol R sub O is used to denote the resistivity of a formation which is 100% water wet. Thus, in this case, R sub T equals R sub O. The resistivities of the mud, R sub M, and the mud cake, R sub MC, are also low compared to the resistivity of the flushed zone. This resistivity profile also assumes freshwater mud, but in this case, the formation is a permeable oil-bearing bed. The resistivity of the flushed zone, R sub XO, is high due to freshwater mud filtrate, as was the case in the previous profile. The invaded zone has a mixture of mud filtrate, formation water, and some residual hydrocarbons. Such a mixture causes high resistivity, in some cases equal to that in the flushed zone. Sometimes in hydrocarbon-bearing formations, the mobility of the hydrocarbon is greater than that of water. In this case, an annular zone, R sub AN, with a high formation water saturation, may be formed between the invaded zone and the uninvaded zone. Thus, this annular zone, if present, may show up as a zone of relatively low resistivity. Because hydrocarbons are highly resistive, their presence in the uninvaded zone causes higher resistivity than if the zone contained only saline water. The resistivity of this hydrocarbon-bearing uninvaded zone, R sub T, is normally somewhat less than the resistivity of the flushed and transition zones, which contain freshwater mud filtrate. The profiles we have just looked at assume freshwater mud. In the case of saltwater mud and a water-bearing bed with saline formation water, there is no appreciable difference in resistivities from the flushed zone, R sub XO, to the uninvaded zone, R sub T. This is because the resistivity of the mud filtrate is approximately equal to the resistivity of the formation water. In the case of a saltwater mud and an oil-bearing formation, the resistivity of the flush zone is low because of saline mud filtrate. Away from the borehole, as more hydrocarbons mix with the mud filtrate, the resistivity of the invaded zone gradually increases to R sub T, the true resistivity of the uninvaded zone.
Now let's see how we go about obtaining a quantitative estimate of water saturation from well logs.
We recall from GL 402 that the formation factor F was developed by Archie, who showed that the resistivity of a water-filled formation, R sub O, filled with a water having a resistivity, R sub W, can be related by means of a formation factor F, where R sub O equals F times R sub W. This formation resistivity factor F is equal to resistivity of the formation 100% saturated with water, R sub O, divided by the resistivity of the formation water, R sub W. Archie also showed that the formation factor is related to porosity in a predictable manner. The two commonly used formation factor to porosity relations are formation factor F equals 1 divided by the porosity squared for carbonates, and in the case of sandstones, F equals 0.81 divided by the porosity squared. Archie further showed that we can arrive at a quantitative estimate of water saturation, where S sub W, the water saturation, equals the square root of the formation factor F times the resistivity of the formation water, R sub W, divided by the resistivity of the uninvaded zone, R sub T.
This formula is commonly referred to as the Archie equation for water saturation, and all present methods of interpretation involving resistivity curves are derived from this equation. Now let's see what we need to know to solve the Archie equation.
First of all, we need to determine the formation factor F. Since F is directly related to porosity, a common method for finding F is to apply the two formulas we saw previously. F equals 1 over porosity squared for carbonates, and F equals 0.81 over porosity squared for sandstones.
We recall that porosity can be determined from one or a combination of two porosity logs, neutron, density, or sonic. Formation water resistivity, R sub W, can be found from a catalog of water resistivity values, analysis of produced water from a drill stem test or from a water-producing well. Another method, using charts provided by service companies, involves the SP curve in a clean formation. Since the resistivity of a fluid is a function of temperature, R sub W must be corrected to formation temperature. Finally, R sub T, the resistivity of the uninvaded formation, can be obtained from resistivity logs. We'll examine the interpretation of resistivity logs in a moment. Before we look at them, we should note that although these classic Archie relationships work very well in clean formations, the analyst has formidable problems when confronted with shaly sands. For example, conventional log analysis may overestimate water saturation in shaly sands, leading to bypass production. In your manual, you'll find a full discussion of the shaly sands problem, along with descriptions of several popular interpretation models. Now let's take a look at the interpretation of resistivity logs.
Remember that a dry rock matrix is a nearly perfect insulator, and that electricity can pass through a formation only because of the conductive fluids. Thus, the overall resistivity of the formation depends on the resistivity of the formation water, the amount of water present, and the pore structure geometry. Resistivity logs contain an SP, or gamma ray curve, on the left side of the log display. The resistivity curves scaled in ohms, or more precisely ohm meters, are on the right-hand side of the log, commonly on a logarithmic scale. There are several types of resistivity logs in use today. This is a common type of resistivity log, the dual induction log, that has been run over the sandstone interval in South Louisiana we looked at earlier. Although recorded on a scale up to 2,000 ohms, our curves on this example are displayed on a scale from 0.2 ohms up to only 20 ohms. The dashed curve is a record of the induction log deep device, or ILD, which is designed to read the true resistivity, R sub T, of the uninvaded zone. The dotted curve records the induction log medium device, ILM, which generally measures the resistivity of the transition zone. The dual induction log is commonly run together with a log that has a shallow depth of investigation. In this example, a spherically focused log, SFL, displayed by the solid curve, serves this purpose. The SFL log records resistivities that are strongly influenced by the flushed zone, R sub XO, adjacent to the borehole wall. At the top of the sand, as determined by the SP curve, we see a higher resistive zone, overlying a low resistive interval. At an initial glance, this appears to record high resistivity hydrocarbon overlaying lower resistivity formation water. To confirm this interpretation, we need to know if the resistive interval is porous, because the resistivity could be caused by a tight, low porosity sand. Now let's add a porosity log to the display. In this case, the combination neutron density log that we examined earlier. We recall that the dashed neutron curve and the solid density curve read apparent sandstone porosity. Our high resistivity sand is obviously porous because the neutron and density curves show from 17% to 38% porosity throughout most of the interval. We also recall that separation of the porosity curves, as we see here, with the neutron curve reading low porosity and the density reading high porosity, indicates the presence of gas.
Let's now try to calculate water saturation to see what fraction of the pore volume contains hydrocarbons. We haven't had time in this video to go through the full Archie equation, so let's instead try a quick look method that can provide a close indication of water saturation.
A term R sub WA is used to indicate an apparent formation water resistivity. In the case where water saturation is assumed to be 100%, the Archie water saturation equation can be written as the apparent water saturation, R sub WA, equals the true resistivity of the formation, R sub T, over the formation factor, F. If we assume that the deep induction log curve records the resistivity of the uninvaded zone, we can replace R sub T in our formula with ILD, the value of the deep induction curve. It should be emphasized that R sub WA is only equal to the true resistivity of the formation water, R sub W, when the formation is 100% water saturated, as we see here. Thus, in hydrocarbon-bearing formations, the calculated apparent water resistivity, R sub WA, will be greater than the true water resistivity, R sub W. Going back over our equation, then, R sub WA is obtained simply by dividing the deep induction resistivity by the formation factor, F. Let's return to the log of our South Louisiana sand. First, we obtain the R sub WA for the portion of our sand which is 100% water wet. We identify such a zone here at 12,445 feet, as revealed by the low resistivity readings. Before we calculate the R sub WA, we must first establish a value for F, the formation factor. You'll recall that for sandstones, the formation factor equals approximately 0.81 over the square of the porosity. We thus square the log porosity of 30% and divide it into 0.81. Our formation factor, then, is 9. Now, to find the R sub WA of the water-wet sand, we simply divide the formation factor 9 into 0.4 ohms, the induction log deep reading obtained from the dashed curve. Our R sub WA then becomes 0.04 ohms. Since we determined this value in a 100% water-wet formation, where R sub W is equal to R sub WA, we now have established a value for R sub W as 0.04. The R sub WA in the resistive hydrocarbon-bearing zone at the top of the sand, here at 12,384 feet, is then calculated. We recall that earlier we calculated a porosity here of 30.4%. which is approximately midway between the neutron and density porosity readings. Thus, to obtain the formation factor F, we again divide the sandstone factor, 0.81, by the square of the porosity, 0.304, which equals 8.77. At 12,384 feet, the deep induction curve reads about 12 ohms. Our R sub WA is then obtained by dividing the induction log deep reading of 12 ohms by the formation factor, 8.77, which gives us an R sub WA of 1.37. To obtain the water saturation, S sub W, of a zone, we take the square root of the water resistivity, R sub W, divided by the apparent water resistivity, R sub WA. Thus, the water saturation at 12,384 feet equals the square root of 0.04 divided by 1.37, which equals 17%. Hence, our gas saturation at this depth equals 83%. An R sub WA value can be continuously calculated by a computer during the log run and displayed as a curve on the left-hand side of the log. The R sub WA scale in our South Louisiana log is from 0 to 0.5 ohms, with a backup scale of 0 to 5 ohms when the curve goes off scale. Opposite the water-filled sand at 12,245 feet, the computed R sub WA is close to the R sub WA of 0.04 ohms that we calculated manually. A rule of thumb is that an R sub WA value at least 3 times that of the true water resistivity, R sub W, indicates probable hydrocarbon pay. In the case of our South Louisiana sand, we thus look for R sub WA values over 0.12 ohms, which is 3 times the R sub W value of 0.04. On this basis, we have pay from 12,376 feet to a gas-water contact at 12,408 feet and a net pay of 30 feet. The R sub WA method we just used to obtain the water saturation in our South Louisiana sand required as a first step the calculation of an apparent water resistivity in an assumed 100% water-saturated section of the sand being evaluated. This apparent water resistivity was then assumed to be approximately equal to the true water resistivity.
In situations where we do not have a water-bearing section of the formation, we must use another method other than the RWA method. We can apply the standard Archie equation, but this requires a knowledge of the true water resistivity, R sub W. You will recall that a value for R sub W may be obtained from produced water samples, published catalogs, or from the SP curve.
Let's now attempt to evaluate the hydrocarbon potential of our West Texas well. We focus our attention on the 56-foot thick carbonate formation defined by the gamma ray log. The neutron density combination log we looked at earlier indicated a 28-foot interval of porosity ranging between about 10 and 14% from here to here. Because the well was drilled with saltwater-based drilling mud, therefore a type of resistivity tool called a lateral log was run in the hole. In this case, a dual lateral log system was used, one that contains a shallow device to measure the resistivity of the invaded zone, as displayed by the solid curve, and a deep device designed to measure the resistivity of mostly the uninvaded zone, as displayed by the dashed curve. Our log presentation is on a logarithmic scale from 0.2 to 2,000 ohms. Note that the shallow lateral log reads significantly less resistivity, about 22 ohms here, than the deep lateral log, which reads about 40 ohms here, thus reflecting the influence of low resistivity saline mud filtrate in the invaded zone. The deep lateral log, with its higher resistivity reading, indicates possible hydrocarbons in the uninvaded zone.
Let's now attempt to determine the water saturation of this interval to see if it might be productive. Here we don't have an obvious water-wet section of the formation from which to determine an approximate formation water resistivity. We are, however, provided with an RW value that was obtained from a water sample of the formation from a nearby well. We'll determine water saturation by using the same basic RWA method we used in South Louisiana, where water saturation equals the square root of the water resistivity over the apparent water resistivity. In this case, we'll use a nomograph such as this that you can find in service company manuals. Let's calculate the water saturation here at 5064 feet.
At this depth, we previously determined a porosity of 12% using the density neutron crossplot chart. We mark this value here on the porosity scale for carbonates. Then we obtain a resistivity reading of 40 ohms from the lateral log deep curve. We assume that this value is obtained from the uninvaded zone and represents R sub T, the true resistivity. We mark this value on the R sub T scale. Then we run a straight line through the porosity and resistivity points to an apparent water resistivity scale. The line intersects the R sub WA scale at 0.6 ohms. From this point, we run a straight line through the R sub W scale at 0.04 ohms. This was the formation water resistivity obtained from a sample in a nearby well. Our line now intersects the water saturation scale at 25%. Subtracting this value from 100% gives a value of 75% for the hydrocarbon saturation, thus indicating a productive formation. The well, in fact, was completed in this formation, producing several hundred barrels per day of water-free oil, thus confirming our interpretation.
We have just gone through the manual steps needed to obtain the hydrocarbon saturation in our two examples. For the most part, automatic calculation by computers has now taken over this task.
Computer-processed interpretations range from very sophisticated programs available only at service company regional computer centers to well site computer interpretations, which can address many complex reservoir and shale formation models, to more straightforward formation evaluation programs available for use with personal computers. This is a computer-generated log of our West Texas example. This general interpretation model uses the density neutron, resistivity, and gamma ray logs, along with information on the resistivity of the formation water. On the left side of the log in track 1, the average grain density of the formation solids is recorded in grams per cubic centimeter. In track 2, we see a plot of the water saturation scaled from 0 to 100% in divisions of 20%. Note that at 5,064 feet, where we performed our manual calculation to arrive at a water saturation of 25%, the computer has determined about the same value. Also in this tract, we see an estimate of permeability, which provides an indication of the formation's productivity. We recall that permeability, generally measured in millidarcies, refers to the ease with which fluids flow through the formation. The permeability scale on this display is logarithmic and ranges from 0.1 to 10,000 millidarcies. Total absolute or intrinsic permeability is indicated by this solid line, and the portion of this absolute value, which is effective hydrocarbon permeability, is darkened. In track 3 is a porosity analysis showing total porosity scaled from 0 to 25% in divisions of 5%. Note that at 5,064 feet, the computed porosity is about 12%, which is the same as our calculated porosity. The relative portion of the total porosity which is occupied by hydrocarbon is darkened, and that portion occupied by water is shown in white. In track 4 on the right of the log, on a scale of 0 to 100%, we see a formation analysis showing the clay fraction, a matrix solids fraction, and the porosity fraction in white. Note that our productive interval is calculated to be shale-free. Another model designed for shale formations is based on the dual water concept, wherein the shale fraction of the formation is modeled as consisting of two components, dry clay minerals and the water bound to the surface of the clay grains. Since the bound water is immovable, the volume it occupies cannot be displaced by hydrocarbons, and it is not considered effective porosity. The model then treats the total water as consisting in two phases, the bound water and free water, and arrives at a saturation value for each as well as a value for the effective portion of the total porosity.
Let's briefly look at a computed log over our South Louisiana sandstone interval that uses the dual water model.
On track 1, the gamma ray curve is displayed for correlation. In the next track, we see a permeability analysis, which includes the intrinsic or absolute permeability, the effective permeability to hydrocarbons indicated by the shaded portion, and the effective permeability to water indicated by the white. Here, at a depth of 12,384 feet, where we previously calculated gas pay, an intrinsic permeability of over 1,000 millidarcies is displayed. all of which is effective permeability to gas as indicated by the lightly shaded area. Here at 12,446 feet, where we calculated 100% water saturation, the intrinsic permeability is several hundred millidarcies, all of which is effective water permeability, as shown by the white area. In the next track, a water saturation curve is displayed on a scale from 0 to 100%, with divisions of 20%. We see that the top 18 feet of the gas column contains a water saturation between 15 and 20%, while the lower 10 feet of the gas column is a transitional zone to the gas water level here at 12,407 feet, where the water saturation increases to 50%. The interval below the gas-water contact contains water saturations exceeding 50%, and according to the effective permeability curve, will for the most part produce only water. In the next track, an effective porosity curve is displayed, which shows the portion of the effective porosity occupied by hydrocarbon, as indicated by the dark shaded area, and the portion occupied by water, as shown by the white area. Note that the computed porosity of about 31% at 12,384 feet equates to our manually calculated porosity of 30.4%. On the right-hand track, a formation analysis is displayed on a scale of 0 to 100%, with 10% divisions. The log shows the portion of the formation which is effective porosity, bound water, sand, silt, and dry clay.
Well, this concludes our video presentation on formation evaluation using well log measurements. While we haven't had time to cover the complete subject of formation evaluation, we hope this video has provided you with a basic understanding of how a petroleum reservoir may be evaluated by wireline well logs. Don't forget to read your manual, do the exercises, and good luck.